Hello, everyone. Welcome back to the AAS YouTube channel. And this is part
Hi.
great stuff. Hi there. We got some bandwidth. And I am super happy to have Prateek Mayank with us today. Hi, Prateek.
Yeah. Hi, Frank. Yeah. Thanks for inviting me. Thank you very much.
Thank you very much for agreeing to talk about your very lovely supplement article, which we'll get to here in a minute. And Prateek, where are you located at?
So currently I'm in currently I'm in eastern side of India, but
India.
I generally stay in the western side of India. Yeah.
Okay. Okay. What takes you to the eastern side of India these days?
So it's like getting colder now, but still winter is a little far from. Yeah.
Okay. So weather. Very cool. So we do have a little bit of bandwidth lag as we go here, people, and we're just going to be patient as we go through this because we are communicating halfway around the world to Prateek. So this will be great. And Prateek, what do you like to do for research?
So I'm mainly interested in modeling, MHD modeling. So currently I'm involved in space weather modeling.
Mm-hmm.
And I have also some interest in observations too. So it's kind of mixed up.
Good combination, theory and observation. Very good. And that is going to bring us to this very lovely APJ supplement article. It's open access, people. You can go get a copy for free. Go get it. SWASTi-SW, Space Weather Adaptive Simulation Framework for Solar Wind and its relevance to the Aditya-L1 mission. And Prateek, take us away.
Yeah, thanks. So let me start with the motivation of this work, that what compelled us to start developing a solar wind model.
Mm-hmm.
So we all know that we have become more and more dependent on the space-based technologies, which make us vulnerable to a threat that is sometimes called the space weather events. So the space weather is similar to the terrestrial weather, but with the main difference that it is driven by mainly the solar eruptions.
Okay.
So yeah, so there could be many solar eruptions or the space weather drivers, for example, CMEs, SIRs, solar energetic particles,
Mm-hmm.
and the solar wind being the background of these all space weather drivers. It governs their propagation in the inner heliosphere. That's why it becomes very important to understand and study the solar wind so that we could accurately compute or predict the solar wind plasma properties and hence the arrival of other energetic space weather events.
Cool.
So there are many institutes and government agencies involved in developing space weather forecasting model, considering the gravity of this situation. And on the similar note, we have started developing an indigenous physics-based space weather framework. And this work on the solar wind module is the first steps towards achieving that goal.
Nice.
So additionally, there is also Aditya-L1 going into the space. So Aditya-L1 is the first first Indian mission to study the sun from the space.
Mm-hmm.
So it will be deployed at the L1 point of sun and Earth, and in the near future, most probably in the next year. And so what we have tried to achieve in this work is that we have synthesized the potential observations of the one in situ payload of this Aditya-L1, which is SPECS. And as we'll go and we'll see that what we have done.
Okay.
So so that brings us to the question that what is the question that we are trying to address? So what we are trying to address is that we want to develop a solar wind model that can forecast or compute the plasma properties of solar wind in reasonable computational time with adequate accuracy. So that is the main motive. So due to which we have opted for a two-domain approach. The first is the coronal domain and second is the inner heliospheric domain.
Okay.
So the coronal domain is the semi-empirical domain, which uses an empirical relation based on the observations of the solar surface.
Okay.
And the inner heliospheric domain is the MHD-based domain in which we solve MHD equations to simulate the solar wind.
Okay.
So Yeah, so starting with the solar surface, we use the data-driven input, which is the observation of the solar surface from the magnetogram, that is the magnetogram, which provides us the magnetic field of the solar surface from. So basically, these are line of sight magnetogram, so they only provide mainly the observation is of radial component. So currently, that's the situation. So
Okay.
using the BR, the radial component, we extrapolate the magnetic field from the solar surface to something called the source surface.
Okay.
And we do this by using a potential field source surface model, which is PFSS. The
Okay.
PFSS assumes that the current is zero in this region from the solar surface to the source surface. So we have taken the source surface to be 2.5 solar radius, which is the default value.
Okay.
But we are also planning to have some scheme through which it will be varying uh, depending on the solar activity or the phase of the cycle of the solar activity.
Uh-huh.
So
Okay.
currently by default it's 2.5, it's fixed. So once we have the magnetic field at source surface from where the magnetic field is almost radial, then
Yeah.
we use something called scattering current sheet. The scattering current sheet doesn't assume the current density is zero everywhere. Rather, there is a current sheet formed where now the current density is non-zero.
Right.
So the Stratton gave this model, which is Stratton current sheet model lens. So in SWASTi-SW, in the solar wind model, so basically this is optional. So either we can use only PFSS or PFSS plus SCS. If we go to the first figure, then
Yeah.
we can see that the whole uh,
SWASTi and
diagram of the steps in the SWASTi.
okay. There we go.
Yeah.
Bandwidth.
So yeah, so it starts with the input from the magnetogram, and then we have the PFSS.
Mm.
And from PFSS, we could directly use the WSA relation, or we can go to SCS model, and then we can use the WSA relation. So I will quickly go to the WSA relation in few minutes.
Okay.
But basically, what WSA relation does is it provides an empirical relation of solar wind speed at 0.1 AU, which
Okay.
is 21.5 solar radius, by
Okay.
using the observations of the coronal hole on the solar surface.
Ah,
So from the observation, there
okay.
comes two parameters, which is Fs and D mentioned here.
Okay.
Fs stands for the expansion factor, and D is something which I will define a little later using other plot. So once we have the speed relation at 0.1 AU,
Yes, that's
then we use some other empirical relations of other plasma properties,
okay.
and then we input in the MHD domain of the inner heliosphere. And to solve the MHD equations, we use Pluto code that basically solves us for the MHD equations in a very like fastly. And we have used something called HUX, which is heliospheric upwind extrapolation technique.
Okay.
So it neglects the magnetic field, gravity, and it does everything very fast. But the demerit is that it only provides the speed, and that also in just 2D scenario, not the 3D thing. But it's very fast and gives a sense of what will be the final result, how accurate it's gonna be, or how bad it's gonna be. So we get an initial hunch from HUX.
There you go.
So that we have also tried. So once we do the Pluto simulation, then we have the solar wind plasma properties in the inner heliosphere and also at 1 AU. So obviously our aim is to compute these plasma properties in the near Earth space, near Earth region,
Yes.
but also near other like Mars and Venus. But the main priority is right now in this work is to forecast the solar wind properties in the near Earth region.
Cool. Very nice.
So now coming to the WSA equation. So
Yes.
WSA equation has been given by, I think, Arj that we have used in 2003. If we go a little, yeah.
Equation one.
So it has, yeah, equation one. So it has many independent parameters. So Fs, we can see the Fs in the denominator and D parameter in the numerator. So the independent parameters, which I call independent, is V minimum, V maximum, the W in the denominator of D, and then beta. So these are kind of So these are kind of independent parameters which we need to tweak to our accordingly, so that we get the best results from this.
Okay, got it.
And Fs is the definition of the expansion factor, that how much the flux tube, magnetic flux tube is expanding. So that is governed by the Fs.
Yep.
So the speed. So what WSA says that the speed at 1 AU majorly depends on the expansion factor and D in such a way that it is inversely proportional to the expansion factor and directly proportional to the D. So D is basically, if we go to the second plot, then I will be able to like define the D, because it's kind of little complicated. The D. So basically is D is the information which we use of that from how inside the coronal hole that magnetic field line is coming.
Okay.
So that is the D parameter. So if we look at the C plot of figure 2, then we can see that the green area is the coronal hole, and the cyan and orange are the open magnetic field lines that is coming out from the coronal hole on the solar surface and reaching to the sub-earth points. And the horizontal black dots are basically the sub-earth points if we project those on the 2D. And assume that we are at Earth and then seeing the solar surface, then we will see this plot.
Okay.
So the red dots are basically the foot points of these open field lines at the coronal hole area or at the solar surface. So D is the minimum distance of this red point from the periphery of the coronal hole. That is the minimum distance from the red point to the nearest boundary of this green area. So that is D.
Okay.
So we have expansion factor, we have D from the extrapolation of magnetic field using the magnetogram. And once we have those, then we have to take some values of those independent parameters in the equation 1. So we have taken a set of independent values which are based on the long-term studies done by other groups, and the V minimum, V maximum, W, and beta. So we also found that this independent parameters is a kind of obstacle in making this equation more generic. So it is dependent on the time period of the solar activity. For example, if we take the W parameter here, so the main role of this W is to normalize the effect of D. And D, as we define, we saw that it could be dependent on the grid resolution that we are taking. Because if we are taking the lower grid resolution, so the values between those points will be larger. And the distance between those points will be larger. And hence the W will also vary. So it's kind of dependent on the resolution that the user is taking. So to get rid of this independency in the W parameter, we try to make it like generalize it so that there is less and less obstacle in making these WS equations not generic. So what we noticed is that there could be many ways to normalize the effect of D. But what we notice is that if we take W as the median of D, which is very simple, we can take mean or median or something else. So we notice if we take the median, then we are getting some sort of good answers for most of the Carrington rotations. So we stick to that, and then we see that the results are getting good. So we have generalized it. It's not like it's one value for every Carrington rotation or every solar activity. But still the V minimum, V maximum, and beta. There are three things which are still independent. So in this paper, again, we tried to use HUX to find the optimum value of beta for which we get the best input to the MHD domain and hence the good final results. So the next two plots are showing that how if we vary the beta, this the speed profile, which is VR in equation 1, gets changed, which is the WSA. So we can see that there are mainly two important features here. One is the initial one, where all the field lines are at one point almost together,
Yes.
and at the end of the plot, on the right side of the plots,
Mm-hmm.
they are almost parallel and they are separated.
Let me ask you
So
a question.
if we see the yeah
Why does the x-axis stop at 12 degrees? Why not 100 degrees or any other number? Why 12?
because we can see that they have become almost parallel and they are in the same. So we are not going to see any interesting feature even if we go beyond 12. So
Okay.
we have stopped just 12. So it
Got
will just propagate itself
got it.
in the same manner.
Physically, it goes on with the plot here.
So the
Okay.
yeah
I'm good.
yeah. So the x-axis is D, and the color designates the value of the expansion factor.
Right.
So we have two things, expansion factor and D,
Okay.
and the other beta and W is there. So there are two main features here, at the initial of the plots and at the end of the plots.
Mhm.
And there's a sweet spot between these two. So we can see if we vary expansion factor, or if we vary the D, then we see change in VR in this sweet spot. So
Yeah.
if, for example, if we go to the bottom three plots, then we can see that there is an increase in VRIN for only that specific reason. Otherwise, the VRIN is constant, and VRIN is constant after some values and before some values.
Got it.
So we can see this plot, which is the figure 4. We have shown that if we take the W value as the D median of D, then we notice the same features. So
Okay.
in the figure 3, we were not constraining the W from that, and now we are constraining W with the median of D. So the
Okay.
same feature is being observed. So it means that if we take W as a median of D, then we are in the sweet spot where the velocity profile is dependent on Fs and D both, which is kind of necessary if we are using both as an observation. So the velocity should be dependent on both. So that was the argument that we gave in this work, and we used W as the median of D, and we kept on going. So
Okay.
the next thing that we did is that we used HUX, which very fastly computes the speed profile by extrapolating from the point 1 AU to 1 AU.
Yes.
And then we compared it with the OMNI data, the observations at the L1 point. And then we tried to optimize the value of beta. So we took 5 Carrington rotations. If we go to the table 1, then we can see that we have taken 5 Carrington rotations. And so figure 5 is also very interesting.
Yep.
So if we see the table 1, then we have 5 Carrington rotations and their corresponding optimal value of beta based on we have taken a window of beta which goes from 0.7 to 1.25 and 0.75 to 1.75, and we have used Pearson correlation coefficient, root mean square error, and something called normalized standard deviation to find a score. And the score for which we have the minimum score gives the best fit. That's the argument that we have given. On the basis of that, we have found the optimal value of beta for different CRs. So it's not like forecasting, but it's like assessing for what value of beta will give the best results. And then we can use that to get the best plasma property results at 1 AU. So, and we also noticed that there is no pattern for if we see that 2053, so it's in like more in the solar minima region, and if we see 2104, 2104, it's more like near the solar maxima region. But there has been no pattern, so we couldn't find any pattern, and the plots also show that there is no any linear pattern in this, that we can say if it is solar minima, then we can take lower beta value. If it's solar maximum, then we get greater beta value. So it's not like that. So we kind of stuck here, but I think some more pattern recognition techniques might help in the future works also. So
Yeah.
that's also interesting that we like to do.
Cool.
So once we have the optimal value of beta,
Okay.
and we are taking W as the median of D, then we have the optimal velocity input for the MHD domain.
Yes.
So from there, we started using other plasma properties empirical relation. For example, let's say now we have the speed profile at 0.1 EU, but we don't know the density profile. Uh, we have the magnetic field extrapolated, but there is also one problem called the open flux problem, that
Right.
what we extrapolate and think that we are getting actually is lesser from the real observations.
Mm-hmm.
So we also try to like overcome that challenge by making it dependent on the velocity and using some observation based maximum magnetic field corresponding to the speed that we actually see.
Okay.
So if we go to the equations,
Mm.
then we have used the conservation of kinetic energy to give the density profile. And then we have used a velocity dependent magnetic profile. And for the BR and B phi follows from the Kepler relation of the solar wind.
Okay.
Yeah.
Yeah.
So, so actually it's, it's
It must be
equation
farther.
9.
Yeah, I was going to say it must be
Yeah.
farther down. Did I miss it? I must.
No, I think it's equation 9.
I think I missed it. Okay. Let's go to equation 9. There we go. It was just past the.
Oh, yeah.
Yeah, here we go.
So these are the empirical relations that we use, to get the initial boundary condition for the inner heliospheric region. So,
Mhm.
so we have the speed profile from WSA relation,
Yes.
and now we have density profile or the initial density profile, and then the BR and B phi.
Yeah. Mm.
And we have taken the constant pressure for simplicity. We have taken a constant pressure of 6.6 nanopascal, which is also based on the kind of interpolation as well as some observations
Oh,
based thing. We have constrained through that so that it's more reasonable, more closer to the reality. But obviously, it's not constant. But for simplicity, right now we have taken it to be a constant.
sure.
So the another thing that is very challenging to get rid of this independent, like for different Carrington rotations, people use different values. So that's the one thing that we need to go ahead of that, so that we have a generalized way for all the Carrington rotations or solar activity.
Okay.
The one thing is the how much the solar wind streams are rotating from the solar surface to the 0.1 AU, if you are taking the semi empirical or WSA relations. So that's the important thing. So what we have tried to get in equation 8, what we are trying to address is that we
Okay.
are trying to make it generalized, and
Mhm.
it is dependent on the minimum speed of the solar wind at 0.1 AU. So that
Yes.
because the minimum speed will move or will cover more angular distance in the longitudinal frame in the phi direction, because it's moving slower, so it will rotate more. It will
More.
cover more angular distance.
Uh-huh.
So and plus it has higher density. So the slow solar winds have higher density, means
Mhm.
they like kind of bulky, so they can push others
Yeah.
and keep their effectiveness. So this alpha, which is by which the solar wind streams are rotating from solar surface to 0.1 AU, is dependent on the time period as well as the distance, which is 20.5, because it's going from 1 solar radius to 21.5 solar radius,
Okay.
and inversely proportional to the slow wind speed.
Mm.
So it comes in the range of around 6 to 9 degrees, or sometimes even 10 degrees.
Okay.
So they are, yeah. So it's still the fast and slow are moving at the same angle, which is not very true. But
Right.
right now we are stuck here. But we are also thinking to make it more generalized, that the
Sure.
fasters and slowers have some different angles, or to be more physically accurate. So
Very.
now once we have all those things, that the solar wind streams have rotated, they
Mhm.
have changed their longitude and latitude, only longitude, And we have density profile, we have magnetic profile, we have density, velocity, and we have pressure. Now we only need the MHD equations,
Right.
and yeah, so it will solve the MHD equations, which are the equation 4, 5, 6, 7.
Yes.
And we have taken the gamma, which is the specific heat ratio, to be 5/3, which is 1.667.
Okay.
So by default, this is the value, and this is also the by default value in Pluto code. And we have also studied that what will happen if we change it. But currently, this is the default value. And the
Yes.
default value of V minimum, V maximum is 250 kilometer per seconds and 650 kilometer per seconds that we have taken, we have seen in the WS relation.
Right.
And one point that I would like to emphasize here is that we have the default value of beta 1.25, but in this work we have used those optimal values we have, which we have optimized using the HUX results. So once we have those initial conditions for all the 5 Carrington rotations, then we solve the these MHD equations, and then we get very nice plots in the inner heliospheric regions,
Yes, you
and
do.
as well as the velocity profile, other profiles at 1. So if we go to this next plot, please. And,
Pretty pictures. Nice.
yeah.
Just
I
bandwidth.
think there is a, again, like, yeah. Oh yeah. So these are, I like the section, the subplot B. That's my favorite in this paper.
This one.
Yeah. So that is basically, yeah, this one. So that is basically the expansion factor in the logarithmic scale. And A is the D profile.
Yes.
So
Okay.
what we are seeing is we are seeing
F.
the theta and phi at constant r. It's in spherical coordinate system. The r is 0.1 AU,
Okay.
and the A plot is the D parameter, B plot is the expansion factor, and
Yes.
from A and B plus WS relation, we get D, and
Yes.
from D, we get C. So basically, these are giving the information that what is the initial form of the input when we are putting in the MHD equations.
Yes.
So if we put these, then we get the plot, the figure 8. Sorry.
Okay. Let's go to figure 8.
So figure 8 is basically giving the information that how the overall structure of the solar wind is formed in the inner heliosphere. So if we focus on the top plots, the subplot A, B, C, those are corresponding to the VR, the radial component of the velocity.
Yeah.
And we can see those spiral structures forming. We have lower speed in closer to the equatorial region and higher speed if you go near 60 degrees. And plus in the subplot C, which is again the theta phi coordinate at constant R1 AU, we can see there is a structure which is corresponding to the current sheet that is forming.
Nice.
And we can see that the speed is lower in this current sheet region. And in the subplot D, we can see the magnetic field is the lowest in this current sheet region, because that is the current sheet region where the polarity inversion is taking place. And again, the subplot E is the density. We can see there is a higher density in the current sheet region, corresponding to the slower wind speed. And plus the temperature is again lower. So in the current sheet region, we have slower wind speed,
Right.
we have higher density, we have lower temperature and lower magnetic field. So that's the whole structure of the solar wind. And this is for the Carrington rotation 2081 for one Carrington rotation. For different Carrington rotations, the structure remains more or less the same, but the values may differ vastly.
And the dot,
And
the dots here are the
yeah, correct.
It's Mercury.
So the blue dot, yeah. So the blue dot is the location of Earth. So this whole solution is in the Carrington frame. So the Earth will remain at 0 degree longitude.
Yeah.
And the red one is obviously it has to be Mars.
Yeah.
And the green one is Mercury.
Yeah.
And the gray one is the Venus.
Okay, gotcha.
So, so that's the thing. So once we have this whole plasma properties from 0.1 AU to 2.1 AU, which
Yes.
is the domain range, the radial range of the domain of the in the computational setup. So we have all the plasma properties. And
Yeah.
now we like to validate that what we have got from the observations to make sure that what we are doing is actually correct.
Nice.
So to validate the results, we have compared our the data, that is the computational data, with the 1 hour averaged data of the OMNI.
Okay.
So if we go to the next plot, then we can see that for 5 Carrington rotations, we have done this for the speed profile, and we have also done it for the other plasma properties also. So coming to the speed profile, we can see there are 5 Carrington rotations and
Yeah.
there are multiple lines. So yeah, so the
Yeah.
gray one is for the observation, that is the hourly averaged OMNI data. And
Oh.
the blue one is the results from the MHD simulation, that is basically the SWASTi-SW. And the red one is from the HUX. And we can see in all these 5 plots, the surprisingly HUX is also giving very good results.
Yes,
So
it is.
that shows that even very simple models can give very accurate results in
True.
most of the cases.
Yeah.
And if we go to the plot corresponding to CR214, then we have compared two different magnetograms, which acts as an input to the model. And the blue line is the default gong magnetogram, whereas the green line is corresponding to the HMI magnetogram on the SDU. Though it's only for only one Carrington rotation in the subplot D,
Yes.
it's yeah in the figure 9, yeah. So it's not easy to conclude from only one CR, but we have compared the gong and HMI and found that the gong magnetogram gives better results from this two domain approach results.
Okay.
So coming to different other plasma properties, for example magnetic field, density
Wow.
and temperature.
Was
So we noticed something that is very nice, that the magnetic field from the empirical relation that we took just to overpass the open flux problem is giving the magnetic field order very accurately. So the features are not matching very perfectly, but the order is good and the overall match is also nice for
yeah.
magnetic field. And this is for the magnitude of the magnetic field.
Yep.
And if we come to the density and temperature, then we can see that the model is overestimating the density and underestimating the temperature for the default value of specific heat ratio, that is gamma is equal to 1.67.
Right.
So what we did is that we changed the value of gamma. We took a range. We went to 1.5. We also went to 1.33, which is 4 by 3. So we noticed that if we decrease the specific heat ratio, then the density is decreasing, temperature is increasing. So it is providing the intel that if you change the specific heat ratio, then you can get better fits for density and temperature, which you are not getting right now for 1.67. But we can see that it's not true for all the longitude. So it could be true where there are peaks in the velocity profile or magnetic profile, and it could not be true where there are minima.
Yeah.
So it also gives a sense that the if you take a varying value of specific heat ratio depending on the density or the solar wind speed, then that could be more wise way to get better fits for density and temperature. So that is also one thing that we'll be looking forward to uh, like do it and see whether it's working fine or not to get the varying value of specific heat ratio. So currently for the default values, we are getting a good fit for speed profile from magnetic field, and we are overestimating the density and underestimating the temperature.
Yes.
So that's the thing. So once we have validated for 5 Carrington rotations, and there's also one thing that we have taken the ideal MHD approach, and we know that for the solar wind in the inner heliosphere, it's not collisional, it's more or less collisionless. So the isotropy breaks there. So it's not isotropic.
Right.
So it could be also that if we take some other techniques where we have something called P parallel or P perpendicular, then also we can get good matches.
Okay.
So this is the overall result of the SWASTi-SW.
Nice.
And then we try to synthesize the potential observations of one of the payloads of this Aditya-L1.
Yeah.
And to do that, we focus more on stream interaction regions.
Okay.
Because we know that in the solar minima phase, most of the geometric storms or uh, the space where the drivers that are responsible for geometric storms are mainly coming from the solar wind interaction regions.
Yes.
And that is one thing that if we are simulating solar wind, then we should be addressing the SIRs, because SIRs getting formed by the interaction of fast and slow winds. So that is the one thing. So we focused on SIR, and we noticed some peculiar features in 3D, because the aspects, which is the in situ instrument in the Aditya-L1, has the novelty of multi-directional features. It has multi angles that it will getting the in situ measurements, as well as it has some differential properties that it can differentiate proton from the alpha particles. So these are the things which are USP of aspects.
Nice.
So the one thing that we noticed, if we see SIR, and we see its different features in R, theta, and phi, then there is a peculiar trait corresponding to each and every SIRs.
Okay.
Not each and every, but whatever we did for the 5 character notations, in mainly in all of them, we notice this feature. So if we go to the word plot.
11. Or do you want 12? This is the geometry.
Yeah. So this is the schematic diagram of showing the so aspects has also 2 subsystems, THA1, top hat 1, and top hat 2. So this top THA1 and THA2 corresponds to the subsystem Swiss of aspects. So aspects is little complicated, and I really thank the all those ISRO centers which helped us in getting this plot. So it is the recent plot, and which is very easy to understand. So there are many detectors. So the A is corresponding to the THA1 and B is corresponding to the THA2, and they cover it's like they cover 2 different planes. So THA1 is covering R theta plane, and this THA2 is covering the R phi plane.
Yeah. Okay.
Whereas C is showing the location of this aspects or the Aditya-L1 once it's deployed. So it will be in the L1 point. Obviously, it will be haloing. It will be following a halo orbit around the L1 point.
Right.
And plus, it won't be at phi is equal to 0 in sun centered frame. Sun centered frame. So it will be like varying from -7 to 7 degrees. So if we put Earth logo at the Aditya-L1 location, then this will be the overall picture that will be seen. So we have formed 3 computational planes to synthesize the observations of aspects or the Swiss aspects. So A, B, C are those computational planes.
Yes.
So they are not spherical; they are like in the Cartesian ones. But the simulation has been done in spherical. Just to show, I have shown, because there is not very good ways to show through the eyes. So I've just made it like A, B, C, and the Cartesian frames. So we have R theta, R phi, and theta phi planes, 3 planes, and then we have similarly, So this is the plot of which I was talking about, that there is a peculiar trait corresponding to SIR. So this plot is corresponding to SIR of 2081. So if we can see the velocity profile here, that there is a velocity gradient. Initially, the velocity is around 250 kilometer per second, and it has gone up to 560, 570 kilometer per second. So it's a mild not very intense, but mild and isolated stream interaction region. And we can see S, S prime, F prime, and F, where S is the slow solar wind, F
Okay.
is fast wind, and
Okay.
S prime and F prime are the interaction regions.
Okay.
And the magnetic field intensity is getting increased,
Cool.
density is also getting increased. So these things we
Yes.
know already from the observations, and these are the main algorithms to detect SIR actually. So
Mm-hmm.
there's also fluctuation in V phi. So that's from where the things start getting interested.
Mm.
So what we did is that we take the averaged on those computational
Average.
planes that I just showed earlier,
Uh-huh.
and we take the proton flux, which is rho v r or rho v theta, rho v phi in those three computational domains.
Yeah.
And what we noticed is that corresponding to those SIR region, that is S prime and F prime, the interaction region, there is
Uh-huh.
an upsurge in the radial component of proton flux, which is obvious, but there is a directional switch in the theta direction.
Yeah.
That yeah. So earlier the proton was coming from one direction, and then it was coming from other, and then it started coming from the one direction.
Wow.
So that's the thing, that it is changing its direction. Means there is a turbulence there, obviously in the interaction region, and in the phi direction, uh, it 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 fluctuates rapidly. It's not
Yeah.
like one switch, so
Yeah.
it's changing its direction again and again. So if we just see the proton flux coming from radial, azimuthal, and meridional planes, then
Yes.
we can say that yeah, if these are the features, then it could be an SIR. So
Okay.
this feature can be used additionally to the increase in magnetic field and density to get more reliable detection techniques of the SIRs in the
Mm-hmm.
observation. So
Cool.
we are also planning to do like comparing this features with the observations for some long-term study and see whether if it is uh, actually different CRs on the long term is showing these properties. That will be like interesting to see.
Cool.
And once the Aditya-L1 goes, this will be very nice to study. So there are not many spacecrafts at L1 which has multi-directional observational capability. And
Right.
once it goes, then it will be really nice.
That'd be really
So
cool.
just to summarize everything, so we have used two-domain approach and the semi-empirical WSA relation plus
Uh-huh.
MHD simulation using Pluto code.
Yes.
And we are computing the plasma properties in the inner heliosphere by using the observations of magnetograms like GONG and HMI. And we are getting good match for velocity and magnetic field in some sense.
Mm-hmm.
And we are overestimating the density and underestimating the temperature.
Yes.
So currently, this is the scenario that we are in. And from here, we are trying to improve it further. And plus, once we have the background, that is the background solar wind, and now we are injecting the coronal mass ejection also to estimate their arrival time, their duration, and their intensity.
Okay.
And then we'll also be focusing on particles in the later future. So that's the thing.
Cool.
And at the end, obviously, I will like to acknowledge that obviously the co-authors and the Bhargav Vaidya, who is also my PhD supervisor, and Devedu Chakrabarti, who
Mm-hmm.
is the PI of the Aspects instrument, and obviously the different ISRO centers, which also helped us in understanding the aspects and synthesizing its observations using simulations.
Mm-hmm. Very cool. Very nice. Very nice. That's really cool. Thank you for walking us through your very lovely article. That was nice.
Thanks.
Yeah, and you touched a little bit there on future directions on where to go. When does the satellite launch? What is anticipated launch? I think it's 2023.
Next year, most probably next year.
Yeah, 2023 sometime. Yeah, very cool.
Yeah.
So although you did touch on it a little bit, what do you think are the, where do you think we go over, let's say, the next 2 to 5 years, particularly after launch, with understanding this, with, bringing the density down, bringing the temperature down, getting those a little better. So where do you think we go over the next 2 to 5 years on this problem?
Yeah. So once the Aditya is launched from the in situ, what we can do is that we can use or opt different techniques, and then again use Aditya-L1 to check whether we are getting good results or not.
Okay.
So if, for example, if we change from ideal MHD to something, let's call some different methods, and then we can again validate those results. And plus the Aditya has also some remote sensing instruments like coronagraph, spectrometer. So these are also things we can also use to observe the CMEs, the initial phase of the CMEs, and then again use those observations as an input to simulate the CMEs in MHD simulations.
Right, right. Cool. Very nice. Very cool. Well, I look forward to seeing this develop
Yeah, sure.
next couple of years. It'll be very nice. Very cool.
Yeah, yeah.
Prateek, thank you once again for walking us through your very lovely article.
Yeah, thank you once again for inviting me here. So it was like really nice to having a chat.
Yeah.
Thank you very much.
You are welcome. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.